Okay. So the last class there was a small error which was pointed out by who is not here. Well, it's not a serious error. We were considering this set, right? F. This is what we're considering, no? F such that mod f of x minus f of y is less than or equal to m times mod x minus y. Okay? And we want to show that this is, I mean, where this is, say, let's say it's n or something. Okay? We want to show that this is nowhere dense. So we want, if you have a function here, we want to intersect with the complement. So something which violates this condition is what we want to show. Okay? I mean, if you have a function, you have another function which is given by that whatever that linear, I mean, piecewise linear functional, and something with a steep slope. Okay, so we got that function, and that is at a distance epsilon or arbitrary closed distance, and that should be in the complement. That should be in the complement. This condition has to be violated. So this condition has to be violated for some point. That's all. But I said that this is violated for all points, which is not true. I mean, it is violated. It is on the line. But when it is on the line and some other point is somewhere, it's not violated. So the statement is not exactly correct, but we have to say that it is just violated. Not that the other inequality, this inequality is true for all xy, which is not true. I made the statement in the end, which is not true. So we will see one more application of Baire's theorem, maybe two more application of Baire's theorem, and we will use it later. So this proposition X be a complete, to apply Baire's theorem in a complete metric space. And we have a sequence of Fn functions from X to, you can take C or R, doesn't matter, C continuous functions. Okay, and Fnx converges to Fx. I mean, this is for all n in n. Okay, we have a sequence of function. We have a sequence of function which are continuous functions. Okay, and X is a complete metric space, and Fnx converges to f of x for all x in x, pointwise. It's not a uniform convergence. If it is uniform convergence, f is also continuous. So it is just pointwise convergence. So then D equal to all those points x in x such that f is not continuous at x is a meagre set. What is the spelling? Is it right? What is the spelling? GUEGR. Okay, right? Okay, I'll remember that. Okay. It's a pointwise convergence. So the limit need not be continuous, but still the points of discontinuity is very small. Okay, very small. It's a meagre set. Okay. This says that meagre set means it's a countable union of nowhere dense subsets. This implies the complement, where the points of continuity is a G delta dense set. That's what it means, right? This implies F is continuous on a G delta means it's a intersection of open sets, countable intersection of open set, continuous on a G delta dense subset. Okay. G delta we defined in the exam. Okay. It's a section of G delta. It's just it's defined in the exam. In the exam question paper, it is defined. G delta F sigma. F sigma means countable union of closed set, countable intersection of open set. Okay. It is just delta comes to the definition. There is no delta, there is nothing delta. Okay. Okay, so we want to prove this D. For this, we make the following definition. We want to formulate continuity in terms of something called oscillation. Okay, so to define this in X, we define, I don't know what is the right notation. Okay, I use this delta X, delta R at X. This is just for to define something else equal to supremum of y z in bxr, the open ball of radius r around x, y z, mod of f of y minus f of z. It is just this difference. Okay. This is delta r given r greater than 0. For r greater than 0, you define this, okay, delta r to be this. So we fix a x, then we define delta rx is just this supremum, which of course appears in the definition of continuity. It is just these things, and you take the supremum of all these over this open ball. Okay. Notice that this is decreasing. Delta rx decreases as r, as r increases, r goes to 0. Huh? I will take the infimum, that will be the oscillation. Okay. Then you define oscillation of x at x is equal to infimum, which is just the limit basically, which is just the limit, infimum of r greater than 0 such that rx. I don't know what is the right. Maybe is there, have you seen it in the book? I don't know what is that. I just used delta r, just came in my mind. Possibly there is a better notation for that. Okay. Huh? That's also possible. It is just to, it will be easier for us to say something. Okay. You can say that. There is nothing wrong with this notation. Okay. Okay. So oscillation is defined to be this limit of this as r goes to 0. Okay. Which is just the infimum of this. Okay. No. Which implies this. Then this proposition ends here. Then I said that this means this. This means, that means, it means this. No. These things implies D is meagre. Pointwise convergence on a complete metric space implies D is meagre, which means this. Meagre means it's a countable union of nowhere dense subset, which means the complement is a countable intersection of, they are all closed set. So intersection of open dense set. So this is a G delta dense subset. That's what I said.
Does not imply that FD is also.
What is FD?
F is the continuous function. F of the set, like the range.
Yeah, need not be.
Even in this.
D is meagre, F should F of D be somewhere. Could be anything. Right? F is, F is in C. Yeah, there is nothing about it. No statement about it. Huh? F of x, F of y minus F of z over this. Do we need bounded? All this happens? I don't think so. F is bounded. Otherwise, Fn's are continuous. No, wait. Fn's are continuous. They need not be bounded. What? On the ball, why should it be bounded? At least on some ball. That's right. But this F is need not be that F. Okay. This F can be. This is for a general F. Maybe G. You use G. Sorry. Delta. One second. Wait. Delta. This is an oscillation of F at X. Oscillation of F at X or G at X. This is not for that F or something. This is for a general function G. This oscillation I'm defining for a general function. So if we have a G be any function from to C, okay, the supremum. If it is infinity, let it be infinity. It's okay. Sure, let it be. Okay. After some time, we are taking the. We are decreasing R to this. If it is continuous, certainly it will be less than epsilon after some time. Okay. So if it is not continuous, then let's take this as the oscillation. Let's see what is the problem. Okay, so this is for a general function g. Okay, once again, where maybe not, maybe not. It's okay. Okay, this is okay. So this is how oscillation is defined. Okay, claim is this. F is g is continuous. This is for a general function g. Okay, this need not be g is continuous, or you don't even take it as proof. We will come to the proof later. Okay, this is just the definition. This is a general discussion. You can include it in proof, doesn't matter. I'm just saying this is general discussion. We will come to the proof later. Okay, so g is the claim is g is continuous at x is equivalent to saying oscillation of g at x. Okay, what is the notation? Oscillation of g at x equals 0. Okay. Okay. So let's first prove this claim. Proof of the claim. So this should be easy, right? G is continuous. So there exists delta given epsilon greater than, there exists delta greater than 0 for any epsilon greater than 0, directed delta greater than 0, such that x is in such that for, I mean, for y in b delta x or b delta xr, f of y minus f of x is less than epsilon. Okay, maybe less than epsilon, it's okay. So this implies for all y is z in b of x, delta, okay, f of y minus f of x, f of z is less than 2 epsilon. This is true for all epsilon. Okay, this implies delta, whatever the delta we define, delta, I should have delta that exists r. Okay, I'm sorry. Let's take r because I have used this delta here. So this is r. Okay. So delta r at x, okay, delta r at x is less than epsilon. Okay, there exists r such that is less than epsilon. For any epsilon, there exists r. For epsilon greater than 0, there exists r greater than 0 such that this happens. Okay, I mean, when r goes to 0, epsilon will go to 0. Okay. This is for arbitrary epsilon. This is true. Okay. I mean, given any epsilon, there exists r such that this happens. Take epsilon going to 0. You get a r and infimum should be 0. It is continuous means this is satisfied. F of y minus f of x is less than epsilon. This is a, I mean, first definition of continuity, you must be knowing it. So you must have, see, there is no, sorry, this is the confusion of g. There is g only. There is no f. Oh my God. There is no f. There is only g. We are talking about g. We will come to that f. We will come to the proof of the proposition later. Okay. Now, I should have started with g itself. F itself doesn't matter. We will come to the proof of the proposition later. Okay. Now, I have just defined for a general function, I have defined oscillation. Okay. Then the claim is oscillation of some function at a point is 0 if and only if it is continuous. Okay. So if it is continuous, oscillation is 0. Just go through the definition, it will come. Okay. The other way is also true. So if oscillation of some function g at x is equal to 0, this means given epsilon greater than 0, okay, there exists a r greater than 0. I mean, that's what it means. You take the infimum over r, that should be 0. So there such that this supremum of y f g, okay. If I write f, that g, okay, g of z is less than epsilon, where y z are in b of y z are in b of x r. Okay. Now, in particular, x is also here. In particular, g of y minus g of x is also less than for all y in b of rx. Okay, this is what continuity means. Okay? Just the definition. Just go through the definition. I should have given it as exercise. Yeah. To be limit. Say it again. That is same as infimum because it's decreasing as r goes to 0. As a, yeah, infimum over r, you want to take a sequence. What do you want? But it's true, it's over all sequences. It's not over single sequences. But it anyway decreasing, you can take a single sequence also. Yeah. Here it's 2 epsilon. Yeah. Yeah, that's what I repeated there. This is just trivial. There is nothing. Yeah, this is if and only if. Yeah. I have just written it again. Okay. Just for clarity. Okay. This should be an exercise. Okay. In continuity. The other non-trivial thing is the following. The other thing. Next thing. Maybe I call it lemma. That is lemma 1. Lemma 2 is yeah. X we are assuming to be complete. X is X. X in X. Relation. And of course, G is any function. G is a continuous function now. From X to C is continuous. Do we need R at any point? I don't think we don't care. Okay. So suppose if it is continuous function, then the oscillation, all those S is that oscillation of G at X less than epsilon. Okay. This thing is open. This is an open set. Huh? Say it again. You have done this in calculus. So just stop it. You have done the whole thing, whole proposition. This lemma you have proven. Okay, so I need not do this. This is open is clear. Okay. But anyway, you just have to go through the definition of open. That's all. So if you have seen it, so otherwise it's an exercise. Anyway, I will orally tell you. You just have to prove it's open. You take any point here, then the oscillation is less than that. Okay. Then you have to produce an open ball around that X, which is completely contained in that. Okay. I think if you take, you have a, see, oscillation is less than epsilon means there exists a R such that something happens that is less than that. You take R by 2, that will work. Okay. R by 2, B of X over R by 2 will be completely contained in that, and that will prove that. Okay. That will prove it's open. Okay. Anyway, it's an exercise. So next lemma is the following. I mean, here we can assume our original statement, Fn from X to C. X is complete, continuous, okay? And Fn(x) converges to f of x for all x. And we have some sort of uniformity in this. That is, given any ball, you can take the closed ball. By closing, you can take the closed ball. The convergence happens on the whole of x. So, but I am taking open ball. But I'm playing for okay, because I want completeness, so I will apply for closed ball. Given any ball P contained in X, any ball of some radius, okay, just another ball B not contained P. Given any ball, there is another ball. Given any ball and epsilon greater than 0. Okay. B not contained in that, such that given another ball and some M or N greater than M in N. For something greater than that also it is true, but this is enough for me. M such that f m x minus f of x is less than epsilon. So is continuous, then the oscillation is going to be 0, right? Yeah, there is no discontinuity. This is for general function. Yeah, this is for a general function. Sorry, there is no. Yeah, I would have used. No, this is for a general function. Sorry, that's what I'm going to apply for. I'm going to apply for this f. So it's not assumed. I'm going to apply for this. So for any function, this is true. Yeah. This is just the assumption of the proposition. So I'm just fnx goes to f of x pointwise. Okay. Anyway, sorry, this is for any f. Okay. So fnx goes to f of x for all x. Given any ball, there is another ball where this thing happens, some sort of uniformity. There is an fmx minus f of x is less than epsilon for all x in b naught. Given any ball, you can find another ball inside that where this thing, this is epsilon close to that. F of x and epsilon x is close to that. Huh? Something like that. Or also it's true. But we need only this. Okay.
Local uniform conversion.
Yeah. Some sort of uniformity. Okay. So proof. Okay. Yeah. Sorry. I didn't sleep. Fnx. Right. Convergence. It's just pointwise. There is no uniform convergence. Then on something you can approximate for this epsilon. This is not exactly uniform convergence something because epsilon is given, a ball is given, then you can do this. Depends on the epsilon, everything. Okay. It is that for this epsilon, you can approximate it for. I mean, this is true for any n greater than m also, but this statement is enough for us. Okay. I mean, this depends on the epsilon also, that ball. Okay, so you have the convergence on everywhere. So you have this ball. Let's take B to be a closed ball. Okay. Bar is B bar is a complete metric space on its own. Okay. Okay. This is a complete metric space. This is a closed subset. So B bar I'm taking a complete metric space. Okay.
You're saying that there exists another ball.
I have to produce another ball in this.
Right.
Yeah. I'm going to produce an open ball inside B naught, which will be in this only.
How can we just take B to be
Without?
How can we take B to be closed?
I'm taking the closure.
Oh, okay.
I'm taking B closure is the closed ball. Yeah. So I have to produce a ball now. I will use Baire's theorem for that. Okay. Now you consider this set. ULFL, whatever. Fn equal to all those x in. X in B naught is we are producing. We get a ball and a m. Given a ball B and epsilon, given a ball B and epsilon, m depends on epsilon, right? Ball, everything. These two depends on epsilon and this. That is true, but I am just writing only for this m. This is enough for us, for our purpose. This will be in the proof. It will be clear that it is true for all n greater than m also. Okay. Exactly. So let's just okay. So we have. So I have to produce another ball. F and B, all those x in that ball, B closure, closed ball, such that F K Fkx minus Flx is less than epsilon for all k and L greater than n. Okay. Okay. This is okay. I'm just defining it like that. Okay. Then Fn is closed, of course, because Fn, since Fn equal to that intersection of all those section of closed set, so it is closed over n such that the continuous function fkx, flx are continuous, modulus is continuous. So this is okay. This is intersection of this, but Fn is closed. I'm just defining Fn like that. Okay. After n, the difference is less than epsilon, less than or equal to epsilon if you want. Yeah. Because you want closeness, no? So you want closed. Less than or equal to epsilon. Okay. So this is all, this is closed, so this is closed. Okay. Okay. Now this happens because since Fnx converges to f of x, or in particular Fnx is Cauchy, this should happen up for some n for each x. Okay. So we have union of Fn equal to that ball. Okay. Right. Okay. I mean, there is nothing specific about the ball. We just want to use it for a ball. So that's why I'm using. So since Fn's are closed, all of them cannot be nowhere dense. So there exists a n naught, okay, such that Fn naught is not nowhere dense by Baire's theorem. Okay. By Baire's theorem, all of them cannot be nowhere dense. Okay. So one of them has to be contain some interior. So there exists a ball. There exists a, I mean, it is closed set. So if the ball is there, then the closure is also there. So there exists a closed ball. There, I don't need a closed ball. There is an open ball is there. So there exists a B naught, okay, contained in B closure. Sorry, contained in F1 of. Sorry, that is what we mean. Okay. So all of them cannot be nowhere. So there exists a ball B naught contained in Fn naught. Okay. I mean, because of the convergence, for some n this has to happen. For some n this has to happen. Because of the convergence, for each x some n it has to happen. So union of all those things equal to B bar. It is this set for all. Exactly. All those x such that this is what you are confused. When you don't mention this that. Okay. So by Baire's theorem, there exists a B naught contained in F1 naught. Okay. Okay. So now it's done, I think. So now for x in B naught, F1 naught, this is in F1 naught, Fk x minus, in particular, Fn naught x, you can take it for any greater than the Fn naught x minus Flx is less than epsilon. I mean, it is true for something greater also, but I take it for n naught, maybe n naught. Okay. Or I should have taken that as yam. That doesn't matter. Okay. Now take L going to infinity. Okay. This implies Fm naught x minus f of x is less than epsilon for all x in that D. That's all. That is what we want. Greater than, no, that's the definition. Fn naught is all those things greater than n naught, that is less than epsilon. What is the definition of Fn? For all k, L, that is the definition. Yes. And take it. Yeah. That doesn't matter. Yeah. But not a kid. Okay. It's okay. Okay, so the proposition is done. Okay. So we want to just use this. Now it follows immediately. It should follow immediately. Now proof of proposition. Okay. So we want to prove the points of discontinuity is meagre set. Okay. So we denoted that by D. D is the set of all discontinuity. That is equal to all those x in x. So set of all discontinuity is where the oscillation of f at x is strictly greater than 0. Okay, so that is same as oscillation of f at x is greater than 1 by n, greater than or equal to 1 by n. D is equal to union of all these things. Union of n equal to 1. Okay, correct? Okay. We have proved that something less than 1 by n is closed set. So, sorry, open set. So this should be a closed set. Okay. This set is closed. Okay. Closed set. All we have to prove that we only need to prove this is a no-variance subset. Okay. Only need to prove this set x in x such that creation of f at x greater than or equal to n is no-variance. I mean, does not contain any open ball, does not have an interior. Interior is empty. Okay. So we just use that. Suppose there exists a ball. I mean, it's not nowhere dense. Means we want to prove it's nowhere dense. So suppose if it is not nowhere dense, that means it contains an interior. So there exists a ball inside that. The proof is over. So suppose there exists a ball which is contained in some again. I mean, let's call it as is the f I have used there. So call it E. Dn. Okay, Dn. Good. Okay. Suppose B is contained in some D n naught or some n naught. Okay. So there exists a ball contained in D n naught. Then we have to get a contradiction. Then there exists another ball, another B naught ball, another ball B naught contained in B, and M greater than, I mean, our epsilon is 1 by n naught. Okay, maybe not 1 by n naught, 1 by some constant times that. Exactly, that's what I'm going to do. We just need to be careful about 1 by n, 1 by 2n, or 1 by 4n, I'm not sure. Okay, so and wait, for some m greater than m in n, such that we have to choose the epsilon. Let's do it such that f of fmx minus I mean, this is there is some uniformity here. That's what we need. Okay, fmx minus f of x is less than 1 by, I think it's 4 and naught. Okay, 1, 2, 3 and naught. I think it's okay. It doesn't matter. We can change it. Okay, no, not any and naught, because we want to get precisely less than this. So that is why we need this one. And I mean, usually epsilon you don't care, but here we want to get precise. We can change it later. Okay. Okay. Now we want to talk about this f of x minus f of y is less than or equal to f of x minus fn fm of x. See here what is the uniformity comes. Okay. Plus fmx minus, there is one more step, I forgot, wait. Now you have the ball B naught, choose, there exists another, I mean, if needed, you can choose something smaller than that, BR, okay, BR, a ball, I mean, another ball, B naught prime contained in B naught, okay, such that for all yz in B naught, okay, mod f of y, fn, fmy minus f1z is less than epsilon, okay, by continuity. B naught prime. Yeah. By continuity. Or since fm is continuous. Yeah. Yeah. The epsilon is 1 by. Okay, let us take it 4 and not. Or 3 and I don't know. 1 by. I think here it is. Doesn't matter. We'll see. We can correct it. We can come back and correct it. Okay. So now we have this f of y minus f of z. F of z is less than or equal to. Here is where we need uniformity. For y and z, we need the same thing. Okay. F of y minus f, that is m, no? My plus f of fmy minus fmz plus fmz minus f of z. Okay. So now let y and z are in this ball, B naught prime. Okay. In this ball, this is less than 1 by 4 and naught. So 3 and naught is what we need. Okay. This is less than 3 and naught. This is 1 by 3 and naught. That is 1 by 3 and naught. Okay. So I think we can have 3 and naught. Okay. Okay. So the whole thing is less than 1 by n naught. Okay. So which is a contradiction, because B naught is contained in that. So which is a contradiction to B naught prime, which is contained in what? I mean, this is a contradiction to say that on this B naught has some radius. Okay. Contradiction to folks that oscillation of what is it? F at oscillation of f at x is less than 1 by n naught for x in B naught prime. I mean, B naught prime is contained in that Dn, no? D n naught, is it? Oscillation is, I mean, we have proved that oscillation is less than 1 by n. That proves oscillation is less than 1 by n naught. Am I confusing? Is it okay? That proves that oscillation, I mean, you have to take this is true for all y and z. If you take the supremum over that ball, that is less than 1 by n naught. So you have a ball where that supremum, this thing is less than 1 by n naught. So oscillation is less than 1 by n naught. So which is a contradiction to this fact. Okay. Or this implies, that implies oscillation of whatever, oscillation of f at x is less than 1 by n naught for all x in B prime, B naught prime, is it? B naught prime, which is a contradiction to B naught contained in that. Okay, done. So any is it okay? So bon. Huh? No. We are not applying lemma 3. For B, we are applying B naught. We get a B naught. Okay. By continuity, we are applying. We get, since f is continuous, I have written. See, since f is continuous, you can always have it. No. Around some x, you can have it. I mean, you take some x. Okay. On this is less than that. Then for any y and z, it should be 1 by 2 of that or something like that. Should be okay. If it is done, I will prove another application of Baire's theorem, which we will use in Fourier series. Is there a problem? Yeah, I'll take a picture. It will be recorded. Very bad, is it? This is good.
Only the picture.
Okay. 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 So in Fourier analysis, I have an application of this theorem, whatever I'm going to prove next. Okay. This is a basic theorem in functional analysis, but this is not very complicated, so we will prove it. Okay. It's a basic theorem. There are other theorems which proof is slightly bit more messy or complicated. There are three basic theorem in functional analysis. You might be, do you know that? Open mapping theorem, closed graph theorem, and uniform boundedness principle. And we will prove the uniform boundedness principle here. Okay. Before that, so from here onwards, for the rest of the class, X is a normed linear space. Okay. NLS means normed linear space, a vector space with a norm. Okay. Okay. It's a normed linear space. Okay. We have a vector space with a norm. Okay. And do you know if it is finite dimensional, all linear operators are continuous? You know that? You know the proof of that? You don't know? Huh? Yeah. If X is finite dimensional,
Not matrix.
norm of the norm of norm of the matrix also. Okay. So the proposition X is finite dimensional. X is finite dimensional. Okay. Then T from X to Y can be anything, any dimension. Okay. Is a linear operator, linear map. Okay. Then T is continuous. T is uniformly continuous. Do you know this? Huh? Okay, we will prove it. No, it doesn't matter. We'll prove it. I mean, it's okay. It's not, these are all simple things to. And yeah. So it is finite dimensional. We'll go through it quickly. Since it is finite dimensional, EI, I equal to 1 to n, contained in X be a basis. Okay. By dividing it by its norm, you can assume that such that norm of EI equal to 1. Okay, for our convenience. Okay, by dividing, these are all, I mean, it's a basis, it should be linear independent, so 0 cannot be there, so norm should be non-zero, so you can divide it, and it's okay, it's all true. So norm EI equal to 1. Okay, now we want claim is, this is the claim. There exists a k greater than 0 such that norm Tx is less than or equal to k times norm x. Okay, then this will imply norm of T x minus y equal to norm Tx minus Ty. Okay, that is less than or equal to k times norm x minus y. Okay, for all xy. Okay, this is the claim. This claim will imply this, that will prove uniform continuity. Huh? It is a middle step. This is what I'm claiming. There is a claim. I don't understand. This will imply that Tx minus T of x minus y, which is equal to Tx minus Ty. Now, without that, how will you prove if it is not linear? Tx minus Ty is to prove continuity, this is less than this. Now, I am not saying from here to here. This implies this. Okay. I am proving from here to here, okay? Norm of Tx minus y. Okay, which is less than or equal to this. You go like this. Okay, that is what I want to. You go like this. Okay, then T of this is less than this. This is what Lipschitz continuous or uniform continuous is. So T is uniform continuous. So I have to prove this claim. Okay. Okay, this you may need it. I will do. Okay. So let x is in V. Okay, and x is equal to summation lambda I EA. I equal to 1 to n. Okay. Then we want to talk about Tx. We want to prove that claim norm Tx equal to T of summation. You can take it out, summation lambda I Tei. Okay, you can, it's linear, so I'm taking it out, which is less than or equal to summation mod lambda I, okay, norm of Tei. Okay, so let K is equal to maybe M is equal to maximum of Tei norm. Okay. Okay. Then this is less than or equal to summation norm lambda I times M. Okay. Okay. But this is just M times norm of X1, where 1 is defined to be for any this, you can define a norm like that, 1 norm. 2 norm if you want, you can like, I mean, if you have any lambda I, you define the norm to be, you can take the supremum of mod lambda I, that to be infinity norm, sum of mod lambda I, that is to be the 1 norm, or you can take the square or something, square, I mean, you can take the sum of the square and take the square root, that is the 2 norm. And all norms are equivalent, that proof you have seen, right? Okay, so this implies this is less than or equal to another K times norm X, that's all. Okay, there will be another K which you club with M and you get this. Okay, so that's all. You can do it in some other way also if you want. So this proves the inequality. The same inequality we are going to prove now. Now we prove for a general okay. So let X this be any non-linear space, okay, and T from X to Y is linear. Then the following one, T is uniformly continuous. I mean, I take so many statements, but I will prove this immediate. Okay. T is continuous. T is continuous at some x naught in X. T is continuous at 0. Okay. 5. There exists a K greater than 0 such that norm Tx is less than or equal to K times norm X for all X. Okay. So 5 statement. Of course, uniform continuity implies continuous. This implies this is little bit. I will write it for you because addition and other things are continuous. It should follow. Anyway, so 3 implies 4. 3, the equivalent of 3 implies 4. So that says that if xn converges to x, xn may be continuous at continuous. I mean, I write 4 as continuous. It's easy to interchange 4 and 3. Okay. Yeah, that's what I'm saying. Here I make it x naught x, and here no, I want it to be 0 at 0. This is x naught. That's okay. Because from here to here, okay. Okay. Now we want to prove that if it is continuous at some point x naught, then it is continuous at 0. Okay. So suppose xn converges to 0. Okay. Then xn, no, xn, I want to prove that it is continuous at 0. So xn goes to 0. I want to prove txn goes to 0. I want to prove, I want to prove 3 implies 4. Okay. So xn converges to x0. Then, it is just the xn plus x naught will converge to x naught. Okay. So txn plus tx naught will converge to tx naught. This implies txn goes to 0. Okay. That's all. Okay. So now 4 implies 5. Okay. From linearity, it follows if it is continuous at one point, it is continuous at another point. You can just add that point. Okay. We are using the fact that addition is continuous. Okay. With respect to this norm, we are using that fact. Okay. Okay, I mean, these are all basic things you should have proved earlier. Addition is continuous. So now 4 implies 5. So what do you want to prove? We want to prove it is continuous at 0, this is satisfied. 5 implies 1 is also clear. Okay, that we have already seen. Uniform continuous is clear. So 4 implies 5 is the only thing we have to prove. Okay, so suppose not. It's easy to produce a contradiction. Suppose not. Okay, there exists. That means that is there exists for all n. For all n, there exists xn in X such that t xn is greater than or equal to n times norm xn. Okay. Okay. Huh? Yeah, what n xn? N xn only I have written. Yeah.
Like it's the same.
What? It's okay. So txn is greater than n times xn. Okay, there exists for any n there exists xn such that this happens. You can bring, I mean, you can, this is a number, you can take it inside. So this implies t xn. Okay, this thing is greater than 1. This goes to 0. Xn by norm xn has norm 1. And that divided by n will go to 0. But that is greater than 1, which cannot go to 0. Which is a contradiction to the assumption that it is continuous at 0. Xn by, once again, norm xn, okay, has norm equal to 1. Okay, so xn by n norm x has norm equal to 1 by n, which goes to 0. Okay, but then t of that this is greater than 1 does not go to 0. So it's not continuous at 0. Okay, yeah, what's the problem?
How you got that?
We want to prove this inequality. Okay, what is that inequality? This inequality. Tx is less than or equal to this for all x. This inequality that does, so this means there exists a k such that this happens. There does not exist a k means for all n this will not be satisfied for some x. Okay, there exists will become for all. Okay, this will be violated for some x. This should be for all x, so it should be for some x. So given any number n, natural number n, there will exist which will depend on that n, that is xn. That is, this is greater than this. Okay, that's what I have written.
Xn also number.
Xn does not. Xn is some number. Xn by norm xn has norm 1. That divided by 1 by n will go to 0. Okay, that has a fixed norm. Okay, that's all. I think the proof is easy, so I will have time to do that. Okay, this is just a remark. We may not need it, but I will tell you. So now you define t is continuous. Okay, suppose remark 1, t from x to y is continuous. Okay, and that is it's a continuous linear map. Okay, and we define norm t. Define norm t equal to supremum of norm tx with norm x less than or equal to 1. Okay, I mean, these are our exercise I should give. So this is first, this is well defined. This is less than infinity. The supremum is less than infinity because norm x is less than 1. We have this thing, right? We have this thing tx. This is continuous means there exists a k such that this is satisfied. Okay. So if norm x equal to norm x is less than 1, okay, then tx norm tx should be less than k. So the supremum is well defined. So this norm t is well defined. So this is a number. Okay. Now it satisfies, this number satisfies. So this is well defined. Okay, this is clear to you. This is well defined. Okay?
Confirm, they're everything at this norm, like that is always.
Yeah. When there is no norm, how will you write norm? This norm. Okay, so if you have a continuous map, then this is finite. A continuous map is also called as bounded linear map. But a linear map is never bounded as a function. It will be unbounded always. You can see, because you can multiply by a lambda, you can take it out as mod lambda, and it will always be unbounded. But bounded means this. This is the definition of bounded linear map, means there exists some, this is bounded like this, this is bounded. It's bounded on the unit ball. That's what it means by bounded linear map. Okay. If it is not bounded, it is not continuous. Okay. Okay. The second remark is actually the supremum. You don't need to take norm x less than or equal to 1. You can take it as norm x equal to 1. Okay. Norm t is actually equal to, indeed, norm t is actually equal to norm tx, such that norm x equal to 1. That is because I'm leaving it as exercise. I'm just orally telling you. This is because this is a supremum. Okay. This is because for anything here strictly less than 1, you will have something. You just, if you have anything, you replace it by norm x. That will be greater than that. Okay. Because you get a norm x is less than 1. So 1 by norm x, when you multiply by 1 by norm x, it will be greater than that. Okay. So anything you have, you get something bigger. So the supremum will be attained in the boundary only. So this is true, that you can check easily. Third thing is norm t is also equal to infimum of all those k greater than 0, such that norm tx is less than or equal to k times norm x. Okay. So why is this true? Okay, I will give a quick proof. Okay. First note, norm tx is less than or equal to norm t times norm x, because this is the supremum. Norm tx is the supremum. So if you can take this norm x here, since x by norm x will have norm 1, right? So on this, that is the supremum. Norm t is a supremum over that. So that will be less than that norm t. Then you bring it back here. Okay. So this is true. So this is true. So this implies norm t is one of those things. It's one of those cases. Okay. Call this in, suppose this infimum is equal to m. Okay. So norm t is greater than or equal to m. Now you have to prove norm t is less than this. Any k is less than that. Now suppose the other way is trivial. Suppose k greater than 0, such that norm tx is less than or equal to k times norm x. Okay. Then t of x by norm x for anything is less than or equal to k. You don't need it. Sorry, you don't need to write. So if norm x is less than or equal to 1, then norm tx is less. Norm tx is less than or equal to k. So this implies taking the supremum. There is no x here. By taking the supremum, norm t is less than or equal to k. So for any k which satisfies this, norm t is less than that. So infimum over, now you take infimum over k, that will be less than that. I will repeat the argument orally. So this implies norm t is less than or equal to m. M, which is the infimum. If you haven't got it, I will repeat the argument. Okay. I'm saying that norm t is equal to infimum of all those k's which satisfies this. Okay. First, using that definition, we prove that norm t is a number. That number satisfies this. Okay. And this infimum is m. Suppose this infimum is m. Since norm t is a number which satisfies this, norm t has to be greater than m. Now we have to prove norm t is less than m, you have to prove. To prove norm t is less than m, any such case satisfying this should be greater than norm t. That's what we have to prove. And that's what is proved here. This is easy exercise. You should better. Norm tx is less than or equal to k for all x, norm x less than or equal to 1. You take the supremum over x less than or equal to 1. That will implies norm t is less than or equal to k. Now you take infimum, there is nothing. Now you take the infimum over k. Norm t is less than or equal to m. Okay, that's all. Anyway, this thing you should write it as exercise, and you should do it. And it is there in any functional analysis book. The first chapter will be this. Okay, that's all. So what we want to prove is the following. Okay, this is what is called uniform boundedness principle, the theorem. Banach-Stein has theorem or something. Okay, this is uniform boundedness principle. Boundedness principle. We will use this in Fourier series to give a counterexample. Okay, Fourier series does not converge somewhere. Okay, I mean there exists point where it diverges. Okay, the statement is the following. Now X is a complete nonlinear space. It is also called as Banach space, complete nonlinear space. Okay, and Ti, I in I, collection of linear operators, bounded, collection of bounded means continuous. Okay, bounded linear operators. Okay. I can be any countable or uncountable, doesn't matter. Okay, it's any collection. You have a collection of bounded linear operator such that norm of Ti x, okay, where such that supremum over I in I is less than m. There exists m for any x, for any given. This x may depend on that. Okay, such that for x in x, there exists a m, which may depend on this thing, such that supremum over I in I norm Tax is less than or equal to m. Okay. Then you have a uniform bound. That's what this is. Then norm Ti supremum over I is less than infinity. Okay. Huh? Any collection. I said any collection. Okay. So if you have pointwise bounded, then this says it's uniformly bounded over the ball or any bounded set. This norm T is the supremum over the ball. Over the ball means you can have any ball also. It is just you have to multiply by that number, by the radius. Huh? Say it again. Yes, using Baire's theorem, of course. Actually, you don't need Baire's theorem. I mean, you don't need completeness here. You can prove it. You can take the completion, prove it, and come back. Okay. So it is bounded linear operators.
By counting, that is
Yep. Say it again. That correct. Bounded means it satisfies that condition. Bounded means norm T is less than infinity.
because for any linear operator in finite dimension that is true, but this X will be infinite.
What's your question? That's your question. Why do we? Otherwise, it's not true. Huh? Say it again. Eh? Well, we never assume finite dimension. This proof is for any dimension. Any finite dimension, it is always true. It's bounded. For infinite dimension, for any in general, it is continuous if and only if it is bounded. Okay. Finite dimension, you don't need it. Okay. So this uniform, if it is pointwise bounded, there exists a m for each x such that it is bounded. This norm Tax is bounded, pointwise bounded. Then it is bounded over the ball, which is what it means by norm Ta is less than this. Okay. Okay. Let Fn equal to all those proof x in x such that t in x is less than or equal to n. Is that right? Is that okay? For all. Okay. Is okay, no? Yeah. You consider this set Fn. Okay, this is less than or equal to this. Ti's are continuous, which is equal to, of course, intersection of all those x in x, Ti x. Norm is continuous, Ti is continuous, so this is closed. Okay, so this set is closed. Okay, this is just intersection of arbitrary intersection of closed set is closed, so this is closed, and we are using the fact that this is continuous, and also norm is continuous. So because of that, this is a closed set. Okay, so Fn is closed. Fn is closed, and for each x there exists some m such that this happens. So that implies that union of Fn n equal to 1 to infinity equal to x. Correct? You tell me. How if you have a continuous function, okay, continuous function less than or equal to some number, is it closed? Is it clear to you? It's closed. Inverse image of closed set is closed. If you have a continuous function, okay, then the inverse, it takes positive value, f inverse of 0 n. This is a closed set. Inverse image of this is closed set because it's continuous function. Okay, here T is continuous function. T norm is continuous function. The whole thing is continuous function. Ti composition of continuous function is continuous function. So this is continuous function. This is so this is closed for each I. Now you take the intersection over all I, which is closed. Okay, that's all. Huh? Yeah. I'm going to prove. You know the proof. Yeah, the proof is trivial. It's not difficult. It follows immediately from Baire's theorem. Okay. Now union of Fnx equal to x. Fn's are closed. Okay, and x is complete. Since x is complete, this fellow Baire will imply. Baire implies there exists a n naught such that interior of Fn naught is not equal to empty. All of them cannot be nowhere dense. So one set should contain some interior. So this has to be this. That is, there exists a B x naught R is contained in Fn naught. Okay. Okay. Now let x is in open. I mean, now norm x is less than or equal to 1. Okay. Now Rx will have less than or equal to R. Okay. Rx plus x naught. Okay. Minus x naught will have norm less than or equal. Is okay. Yeah, this is okay. Well, we can take it little bit less than that. Okay, so let R prime is less than R if you want. Okay, basically, I mean, because there is any less than or equal to or something. Okay, so this is R prime. I think it's okay. Okay, so this is less than that. So now this says that this is in Fn naught. By definition, Fn naught means, so this implies Pi of Rx plus x naught, okay, minus x naught, whatever norm of this is less than or equal to n naught. That's what this is, right? So this implies tx naught will cancel. No. This, pardon, sorry. I mean, sorry. So no. This implies T of No, this says that T of Rx plus this Ti of this is less than n naught, and of course Tx naught, Tix naught is also less than n naught. That's what this says. Yeah. Yeah, that's why I take R prime. Strictly less than R. Yeah. Is that what you want? Yeah. Okay. That's why I took an R prime. These things doesn't matter. I mean, yeah. So that's why I took a smaller one. Okay. So now Tax naught, sorry, this is, yeah, this is okay. Okay. This implies, this is what we naught, Tx naught, Tx. I mean, it will be less than 2n naught by R. Is that okay? R prime if you want. Huh? Ti. I'm just using triangle inequality. Okay. Now this is less than this is less than this. Now T of Rx naught we want. Wait a minute. T of Rx naught we want. T of this is less than